Alright guys, in this video we're going to talk about atomic emission spectrum. Before we start, I wanted to go over what emissions mean. Emission. What does emission mean? To emit. Yeah, it's to give off, right? So make a little note there that it means to give off or to emit something. So atoms emit things. And one of the things they emit from the electron is what? Light. So atoms give off light that comes from the electrons. Now, what we're going to do here after the guided notes today, in just a little bit, we're going to go through and burn different elements in a tube. Not burn them, but pass electricity through it. This one is hydrogen. Well, I think I have it. Let me see if it's already on the slide, then I won't have to. So yeah, this first one is hydrogen. This is hydrogen's atomic emission spectrum. Spectrum just means all the different forms of light. Okay. So hydrogen, when you pass electricity through a glass tube filled with hydrogen, it kind of burns this cool purple color. What we're going to do is view it through a prism. What does a prism do? We talked about it last time. It separates it, right? It separates the light into the individual wavelengths. And so when we view it through a prism, in fact, we're not going to use a prism, but we're going to use a spectroscope, which is kind of the same idea. We're going to see hydrogen has 4 different colors of light. Okay, 4 bands there. And you can see them on both sides here. You've got a red, kind of a blue, and a it's not the best picture there, but you'll see a violet one as well. Okay, this is the spectroscope right here that you're going to look through. So you look through this end right here at this light, and you're going to see that it's broken down into the individual wavelengths. Now, every element on the periodic table has a different emission spectrum. They're all a little bit different. So let's contrast that to heliums now. If you look at helium, and this one's helium, kind of burns this cool yellow color. And the spectroscope, you're going to see a lot of bands. But the main band, which one's most intense, guys? Which color is most intense here? Yeah, it's this yellow color. I want you, when you're looking at helium today, to try and find this dominant band right here. It's the yellow color. And we'll talk about why that is yellow when we do the lab. Okay? So this is examples of emission spectrum. This one's hydrogens, and this one's heliums. So atoms have many electrons that can move from any combination of energy levels. So the light produced from each atom can vary drastically. Every atom on the periodic table has different amounts of electrons, and all these electrons are moving up and down, back down to ground state, giving off light, in any kind of combination. So what we'll study is the atomic emission spectrum of an element, and it includes all the different wavelengths of light that are emitted from the atom. So we saw hydrogen had 4 different bands. Helium has a lot more, and we'll look at even neon. I've got a neon one. It has like 20 different bands of light that are given off. So each element's atomic emission spectrum is unique. Okay, this is a cool fact. Every element on the periodic table looks a little different. This again is hydrogen. It gave off 4 wavelengths of light. So you see a red, kind of this green color, a blue, and a violet. Hydrogen has how many electrons? 1. Has just 1 electron. But as it moves up to higher energy levels, or just to a lower end, just goes up 1 energy level, you can see a red light given off, and you can even see even a violet one. So it can be any kind of combination of colors, but this is what hydrogen gives off. So if you had a sample of unknown material, and you looked at it as you passed electricity through it, and you looked at it through a spectroscope, and you saw these 4 bands, what can you be sure of? That sample must have what element in it? Hydrogen. And so we can use this science here to figure out what is in an unknown sample. And that's what's incredibly useful. Scientists even use this on telescopes. You can put a spectroscope on a telescope and you can shine it at a star or point it at a star and you can get these different bands. So could we tell what elements are present on distant stars? Sure. So we know what elements would be there, even though we're not there. Okay. I wanted to contrast these two words, emission and absorption. Emission means to what, guys? Give off. So it's what's emitted. So if we look at the emission spectrum of hydrogen, it gives off 4 different bands or wavelengths of light. That's what's given off. And so you'll see the background is black, but it gives off 4 different colors of light. So that's what's emitted from a hydrogen atom. Now let's contrast that to absorption. What does absorption mean? It means what's taken in, right? It's what's absorbed, what's taken in. And so absorption is the light that is absorbed by the atom. For hydrogen, the absorption spectrum looks like this. So you see the color in the background, but now where it absorbs light is what color? Black. Because it absorbed that wavelength of light, and so it's black. And so if you see it and you got color bands, this is an emission spectrum. If you see it and it's got black bands, that's called an absorption spectrum. But they're at the same location, so it gives you the same information. Okay, here's a neon sign. Everyone's kind of familiar with the neon sign. It burns this kind of, or it lights up this orange color, kind of reddish orange color. Let's talk about why it does that. So light in a neon sign is produced when electricity is passed through a tube filled with neon gas and it excites the neon atoms. So all this sign is, if you really look at it, is a glass tube. They take all the air out of it, so there's no atoms in there. And then they fill it with what? With neon gas. So the only atoms inside the tube are what? Are neon. And then they hook it up to electrodes, they pass electricity through it. We're going to do the same thing over here in just a little bit. When the neon atoms are given energy through electricity, it moves the electrons to higher energy levels, right? Is that what gives off light?
Sure is.
No, it's when they come back down.
Yeah, it's when they come back down that the light is given off. So you have to give it energy, just like you guys did in the flame test. How did you guys give those atoms energy? Fire. You put it in the flame, right? That heated it up, energy. Electrons moved up into a higher energy level. They didn't want to stay there long, so it came back down to its ground state and gave off that color of light you saw. Well, the excited atoms in this tube will return to their stable state by emitting light. And here is the emission spectrum of neon. How many different bands of light? I mean, it's a lot, right? Well, how many electrons does neon have? Neon's right there. How many? 10. So all of these 10 electrons are going up to excited states, coming back down. And sometimes they give off violet. So there's 3 bands here of violet. There's a pretty good blue section, green. But most of it is where, guys? Yellow, orange, and red. So that's exactly why when you have a neon sign, it produces this color, where it says open here. So this is the neon sign right here, where it's orange and red. Because it's kind of an average of all the different light that the neon atom can give off. Notice how there's more bands over in this region of the spectrum? That's why it looks orange. Okay, so how to view spectral lines? We're going to do it just like this. We have a glass tube here. We're going to pass electricity through it. This one's hydrogen. We're going to look at it through a spectroscope, not a prism, but a prism would work too. We're going to have a spectroscope, and we're going to see these 4 lines for hydrogen. Okay? And hydrogen burns kind of this purple color. It gives off this purple color light. Well, if you look here, the average of all these wavelengths, it's down here in the spectrum, so it looks kind of that color, and not red or orange or yellow. Okay, electrons emit visible light. This is a video that I've got. It's not really a video, but an animation of how this works. maybe. Here it is. Okay, it's on a loop, so it kind of goes continuously, but let's try and figure out what's happening here. That red ball represents the electron. As it goes from 6 to 2, what kind of light was given off? Purple. As it went from 5 to 2, blue. From 4 to 2, green. And from 3 to 2, red. Now let me ask you, why when it goes from 6 to 2 does it give off violet light? That's the largest energy difference, right? So you can see it had to fall down the largest distance. Why when it went from 3 to 2 did it give off red light? That was the smallest energy difference, right? The smallest one gives off red, which is the least energetic color. Let me see. Okay, good. Okay, this is a video. I want to show you this video for a couple of reasons. He does a great job of explaining what an emission and absorption spectrum is. We kind of just talked about it. But I also wanted to show you to introduce this guy here. His name is Mr. Anderson. He has a lot of good science videos on YouTube. He just goes through and explains different science principles, and he does a really good job. And his channel is called Bozeman Science. If you guys are on YouTube and you want to watch some cool videos and learn some good things about science, Bozeman Science is the channel. So anyway, I'll play the video and you can kind of get a sense of what his videos are like, but he does a really great job. Let's watch one on this stuff. Oh, maybe.
Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 86. It's on emission and absorption spectra. If we were to take a gas like hydrogen and put it in a discharge chamber and shoot electrons at it, it's going to give off light that looks like this. If we were to analyze that light, if we were to split it in a prism, it would look like this. So instead of being a rainbow of light, we're going to get these discrete units of light, or these discrete photons that are carrying discrete amounts of energy. And this was puzzling to scientists for a long time. We could also shine light through that discharge chamber, and parts of it would be absorbed. And so this would be the absorption spectra. So most of the light would make through, but some of it isn't going to make it through. And this puzzled scientists for a long time until Niels Bohr finally figured it out. And what's happening, if we look at a hydrogen just in the first two energy levels, is that as the electron goes around the atom, as it jumps to a lower energy level, it's going to give off a photon of light. And for it to move up to that other energy or that higher energy level, it's going to have to absorb a photon. And so there are discrete colors of light that are required for it to jump up. And as it jumps down, it's going to release these discrete colors of light as well. If you hit it with other colors, it's not going to do anything. It doesn't have the right amount of energy. And so this is conservation of energy. Conservation of energy in an atom or in a nuclei when it absorbs a photon, so we call that absorption. And so what does that mean? The amount of energy in the photon and the atom or nuclei before absorption is equal to the amount of energy inside the atom or nuclei after absorption. And same thing applies with emission. And so as we give off that photon, energy is conserved. The amount of energy we had in the atom or the nuclei before is equal to both the photon and atom or nuclei after. Now this is really valuable in science because we could look at what's being given off, so we can look at the spectra of emissions from any kind of element or molecule, and it tells us what elements are going to be found inside it if we know what those energy levels are. And so if you know anything about visible light, it's all the colors of the spectrum. So as we shine it in a prism, as it moves through the glass, different wavelengths of light are going to travel at different speeds, and so it's going to split it into this spectrum. Now know this, that on the red side there's a part of the spectrum that we can't see, that's infrared light, and there's going to be UV light on the other side, and we're just seeing that visible spectrum that's going to be right in the middle. And so if we look at those energy level diagrams, for example, in a hydrogen atom, if we were to hit it with the right color of photon, so let's shine on it the right color of photon, let's say a red photon, watch what happens when it hits that electron. It jumps to a higher energy level. Now let's say it falls down to a lower energy level. What kind of color is going to be given off from that electron? It's going to be that red photon again. But what happens if we hit it with a green photon, for example, and it doesn't have the right color, doesn't have the right energy? it's never going to be able to move. Let's say we hit it with a yellow photon. What does it do? Again, nothing. And so these atoms are being bombarded by different colors of photons, but it has to be the right color. Let's say it's the right purple color. What's going to happen? It's going to jump to a higher energy level. What happens is it falls down to that ground state. It's going to give out that same exact photon. So you can model this. This is a
Okay, so I'll stop it right there, but I think you did a great job of explaining about emission when light is given off, the electron comes back down, or absorption when energy comes in, it absorbs only certain frequencies of light as well. And so I wanted to quickly go through this. It's called quantum theory. In the early 1900s, scientists still didn't understand the relationship among the atomic structure, the electrons, and the atomic emission spectra. They knew it give off different colors of light, but they couldn't really understand how come and what was causing it. Why are atomic emission spectra made up only of certain frequencies of light? So why does hydrogen give off only those 4 bands of light? So we saw that hydrogen's emission spectra had a red light here, a green, and then a blue, and then a violet. Why did it give off only those 4 wavelengths of light? So Niels Bohr, a Danish physicist working in Rutherford's lab, proposed a quantum model of the hydrogen atom that seemed to answer this question. And so Bohr suggested that atoms can absorb or emit energy only in certain amounts called quanta. So if we go back to the Bohr model of the atom, this would be energy level 1. This would be energy level 2. So what Bohr was saying is that atoms can only absorb or emit energy in certain amounts. So the difference from energy level 1 to 2 is a quantifiable specific amount of energy. And you have to give it that much energy for the electron to get up to the second energy level. And then as it falls, it gives off a light with that much energy. So if it's just 1 energy level difference, it might be red. So a quantum is the minimum amount of energy that can be gained or lost by an atom. So this difference right here would represent a quantum. It's the minimum amount of energy. And so there's this rungs of a ladder analogy that works pretty good. If you look at a ladder and this is the ground, can you get your foot to the first step if you only raise your foot that high? No. So nothing will happen. You can put your foot up that high, but nothing's going to happen. You have to give it this much energy to get to the first step, right? Kind of makes sense. Well, same thing in the atom. If you have an electron in the first energy level, can you get it to the second energy level if you give it this much energy? No. So this has to be in a specific amount of energy, and this specific amount of energy is called a quantum. Okay. And so that's what Niels Bohr contributed. But we now know that electrons don't travel around the nucleus in these circular paths called energy levels, as Niels Bohr described. If you remember back to when we were talking about the development of the atomic model, there was these guys, Werner Heisenberg and Erwin Schrödinger. They came up with a new model of the atom. They called it the electron cloud model of the atom. Their results show that it's impossible to know the exact position and direction of the travel of the electrons. So we know that Niels Bohr's model is not correct anymore. So there's this principle in science that I wanted to go over real fast. It's called the Heisenberg uncertainty principle. Yeah, same guy, Werner Heisenberg, that came up with the electron cloud model. He stated that it's fundamentally impossible to know the velocity and the position of a particle at the same time. And so just stay with me just for a second. The only quantity that can be known is probability of an electron to occupy a certain area around the nucleus. We call the cloud. And so Werner Heisenberg and Erwin Schrödinger came up with the electron cloud model. Now guys, in the next few class periods, we're going to talk about the electron cloud. So here's the nucleus, and you got the cloud. We're going to talk about the probability of finding an electron in this space, or the probability of finding an electron in this space. No more of the Bohr model, but in terms of probability maps and how you determine where an electron is likely to be found. So hopefully that helped.